Hello all, welcome to the Abacus Python YouTube channel. This is the Abacus Python scripting learn with the concept lecture series, and this is the 8th lecture in this series. Today we will going to discuss how to create an ODB file. So starting from the what does it mean by ODB till the creation of entire script, all these steps we are going to see today. So let's get started. So first let's go into the introduction, what we are going to discuss it today. So first, what is an ODB? So you may be aware ODB is nothing but the output database, and when it is created from the analysis. It is the output of the analysis by default. So when we submit any job in the Abacus, any calculation we do, one of the output of this analysis will be an ODB file. So there are other files as well. For example, status file, .sta file, .dat file, .message file, .msg file, right? So ODB is nothing but one of the file that is created in the after the analysis. So what does data it stores? Basically, it stores two types of data. One is the analysis data. So analysis data, it depends on what type of analysis you are doing. For example, for the structural analysis, the displacement data, strain data, stress data, these things can be there. For example, when for the frequency or FRF analysis, the frequency related data, acceleration, displacement, strain energy data, right? All this data will be stored in the ODB. The second information, and this is the important information that is there, that will be there, the model information. So model information basically means nodes and elements data along with these surfaces and sets. So why ODB needs to store this data? Because these analysis result, whatever the analysis you are calculating, will be written at this elements and nodes information only, right? And third question we will discuss here is why we need to create an ODB, or what are these cases. So first, ODB size reduction. So as you know, when we do analysis, the output result file will be very huge, and this is one of the drawback, or you can see the negative points of the Abacus, where the ODB file size will be very huge and it is very hard to manage this big file size. So what happens is when designer review wants to review these results, he will not look at all the results. So he wants just the portion of it or the post processed data. So in this case, to reduce the file transfer time, we need to reduce this file size. So creating a sub ODB or a new ODB which has the interested data is very essential. So another case where you want to see the analytical results. So let's say you have created any analytical method or used any analytical method, and you want to visualize this data in terms of the contour and all. So Abacus ODB is the very great tool. Abacus is very great tool to do that. You can do multiple operation when you are in the Abacus viewer. There are multiple options you can use for post processing. So in that case also you can create an ODB. So what data we require to create an ODB? So as I said, we require the model data, base data, that is nodes and elements data. So this is the base information required to define any model. Nodes and element information. Nodes is node labels and the coordinates, and elements will have the element labels and the connectivity along with the other elements with the help of nodes. There will be something called as derived data, which are these quantities are derived from this base data. For example, surfaces basically are the subsets of the nodes. That means surfaces are defined using the nodes. Sets can be of the node sets, element sets. So obviously these are also called the subset of these nodes and elements. Okay, so basically we require this nodes and elements information to create the ODB. So in this example, we are going to consider that we already have an ODB and we want to create a sub ODB from it. So we need to know where this data will be written in the ODB, because ODB can contain analysis data as well as model data. So where this data will be written, it will be written at the instance level. Okay, so some may get confused what is the instance, because when we basically did talk about the Abacus, it says that we have parts, we have instances, we have assembly. So all these three things sometimes we get confused. So let's understand this using one example. Let's understand the hierarchy, because this will be important when we create the ODB. Okay. So let's take an example of the push and shaft assembly. So where let's say we have two parts, bush and shaft. and from this we have, let's say, created the assembly. So these parts, as you can see, these are called as the blueprints of these components. Okay, so bush and shaft, these are the called as the blueprint, and from this blueprint we will create one assembly. Okay, so we'll not directly use this blueprint, so we will make multiple copies of it. So let's say in this example, as you can see, as you might know, shaft will be a single part, but we may have multiple bushes. So number of bushes we will have in this assembly. Basically we use the bushes to support the shaft, right? So we will support the shaft at multiple places, so we will need multiple copies or multiple bushes, right? So now you can see we have created only one blueprint of the bush, but we can create multiple copies of this bush and use it in the assembly. Okay, so what are these copies are called? These are called as nothing but the instances of the parts. Okay, and at these instances only the model data will be written in the ODB. Okay, so there is some convention how these instances are named. So let's, if we have multiple instances, then they will be named as 1 2 3, something like this. And in this case, as you can see, shaft is only one, so shaft dash one, only one. So next we are going to see how to extract this data, then we will create an ODB. So this is this sample script. So these are the steps we are going to complete now. So first we will open the main ODB, then we will create the sub ODB object, and then basically we will access the data from the main ODB, and then we will write the data to the sub ODB, and then we will update and save the sub ODB. Okay, so totally 3 to 4 steps we are going to complete now. So first open the Abaqus in the working directory. So here you can see I have the main ODB here, interference feed, and this is my sample script. So let's open the Abaqus here. So we can open Abaqus CAE as well as Abaqus Viewer, both will be fine. Now Abaqus is open, so let's open the main ODB as well. First thing we have done, so let's open the replay file and copy the import command, ODB import command. So first we need to copy these import statements, right? Then we will use open ODB command. So let me give the ODB object name as ODB, and then we will write main ODB name. So that is what our main ODB name. So just for clarity, let's create the main ODB name, and okay, we don't require this viewport object. Now let's create the sub ODB object. Okay, so to do that, let's open the scripting reference guide, because we cannot record that step. So in the scripting reference guide, go to the Python commands, then search for the ODB commands, and here you will find these commands to create the ODB. So let's write first import statement, and then write this ODB, so session.odb. Let me save this to the sub ODB object, and the options required are name, let me give to the data, then write the path. So for them create this sub ODB name variable. So let me write sub ODB dot ODB, and then refers this name here in the path. So now we can see we have created the sub ODB object. So we can run it also, this one. Okay, this option is not there. Okay, now let me run it again. Okay, now you can see the sub ODB object is created. Now let's access all the instances available. So how do we access all the instances? So write ISN names. Let's create one variable and store the information. So odb.root assembly. Okay, we don't have the odb object itself, so let's create odb object. So session.odbs. Now we have the odb object, so now write ISN names, instance names, and then try to find odb.root assembly, then instances, then write keys. So now you can see it has two instances, bush and shaft. Okay, so let me copy this command as well. Now what we'll do is just for one instance only we'll try to access the data as well. So let's take one instance, let's say ISN1 variable name, and let's say bush instance we will work on. So let's try to print what this instance information will have. You can see when you print it, it will show all the information. So embedded space in which this part is model is 3D. Then it is a deformable body, it's not rigid. Then it has element information in terms of ODB mesh element array. Then it has node information in terms of ODB mesh node array. So let's try to copy these. So now now we access the instance. Now I try to extract the elements. So how do we extract is ISN dot elements. So what I did is I just wrote EL, then I type and then I press tab. So you can see that different types of commands are there getting completed. Okay, so now these are the elements. Okay, so what we will do is we'll try to extract the information for one elements. So when you press left square bracket and press tab, then you can see it is going through each element. Let's try to print any element information. Okay, what information does it have? It has connectivity, it has instance name, then it has type, right, and label. Okay, so all this information we need, not all, some of it. So in this case what happens now? So this is the one of the element type, but what happens is sometimes it can have many element types as well. So what we will do is we will create a dictionary, and in that dictionary only we will save the element information. Okay, so let's try to iterate and try to save the information. So let's write element for element in ISN.element. Okay, then what information do we require? We required connectivity, right? So how do we write is let's say con, the variable name, then write element, then write connectivity. Okay, then write label. Okay, then also one more information we required is type. So let's write EL underscore type. Now these three information we required. So element connectivity, element label, and element type. Now let's create one dictionary. So all this information we will store in the dictionary form. So let's create element dictionary variable. Now let's try to store the information here. So let's write one condition: if element type in, let's say, not in element dictionary, that means the first time we are adding the element to this dictionary. So give the key as element type and store the data in terms of list. How do we store the data? So in the list we'll create another list, let's say tuple in this case, not list, and in this tuple we will store all the information, the label as well as the nodal connectivity. Let's create that and put the connectivity, convert this connectivity variable also into the list and add this to the label. Okay, and convert everything into the tuple, and that you add it into the empty list. So this is when we have newly element type we are going to add in the dictionary. But when this information is already, this element type is already available in the dictionary, in that case we will try to append this information. So write append and this tuple. So let's try to run it. Okay, float has no attribute, connectivity. Okay, there is some issue here. Let's run it again. So it will take some time. So now you can check what are the different types of elements are there in the. So there is only one element type available. That's okay. Next we will extract the nodes. So how do we extract the nodes? The similar way we have extracted the elements. So isn dot nodes, right? So let's again try to print some information about one of the node. So node, what type of information does it have? It has coordinates, it has instance name, and it has label. Okay, so similarly what we have done for the elements, do this for the nodes as well. Okay, so again let's iterate for node in ISN nodes, right? And here we will create two lists to store the label and coordinates. We will use different list because simply because label will be an integer type and coordinates will be of the float type. So we don't want to mess with the types because Abacus doesn't take float type of labels. Okay, so just to be sure of the types, let's use this kind of formatting. Again, how do we extract, what information do we extract? First we will extract the label node dot label, right? Then another information we required is coordinates. Right, now let's add this label into this list. Okay, then in the ND chords, let's add this chords, that is the coordinates, and again convert this to the tuple because it always, the Abacus takes the information in always tuple form. Then again try to run this code just to check whether it is running correctly or not. Again it will take some time. Now you can see the code is running. Okay, now we have extracted the data successfully. Now it's time to write the data to the ODB. So how do we write the data? So as you can see here, we have extracted the data from the instance, but when you are writing the data, you cannot write the data at the instance. You have to always create a part, write the data to the part, and then from the part you create a copy called as instance. Okay, so first let's create the part. To create the part, let's go and check what is the command. So in the ODB commands, we can go for ODB parts. So where it is, okay, here you can see ODB parts. So similarly we have to use session.odbs and part. Okay, so let's copy paste here. We are doing lot of copy pasting. It's okay, we are not cheating. So sub ODB dot part, right? Now let's check what information does it need required. So it requires name, obviously, then the embedded space. So what is the dimensionality of this part that we need to write? How do we get it? From the instance. Then again type, what is it deformable or rigid? So all this information we will get from the instance. Okay, so let's try to get this information. So let's write ISN space and ISN1 dot. We will write embedded space. So this is how we will extract the space dimensionality. Then we need to write type, right? So again we will extract this from the type instance. Okay. Okay. So we require space, time, and name. So name, what is the name? Name also we can extract. Let's write ISN name, ISN1 dot name. Okay, so let's write here name equal to ISN name, then embedded space equals to ISN space, then write type equals to ISN type. Okay, let's try to run this again. ISN name is not defined. We have defined in this, we have written here but not executed. That's why the error. Use up arrow and try to run. Here you can see now the parts has been created. Okay, now we have created the part. Now write the information to the part. That means add nodes and nodes and elements. Again go to the reference documentation, then extract this ODB part object. Then here you will find, so here you will find two types of two similar add elements and add nodes elements methods. So first what it says is you can give the labels and connectivity separately, and the second method says all the information you can give in one go. Okay, so because we have saved our data in this format, we have saved the labels and connectivity in the same variable. So let's use this, right? Okay, so before that let's give the part name. That means so here one thing you need to take care of is we need to first add the nodes. Okay, why we need to add the nodes first? Because when we define the elements, what we usually define, we inside give the node information, right? But if you did not add the node itself and we are directly adding the elements, then it will give an error, right? Because without element there is no element cannot exist. So again for the add nodes also we have two methods, and it requires labels and coordinates, and this requires node data, it requires label and coordinates in the same thing. So we have saved these two variables separately, so let's use this. Okay, so how do we use it? From the myparts dot add nodes, right? Okay, so again labels. So labels is what? Tuple of, see everything we have to give it in the tuple format. Abacus doesn't accept in the list format, because if you know it is a mutability issue. Okay, then what we required, we need to require the coordinates. Again, how do we give it? In the tuple format. So write tuple blah blah blah. Okay, this we have done. Now let's run it. My part is not defined. Oh my god. Okay, so what we have done is we have not accessed this my part, so we have directly executed this command, no? So okay, so my part will be subodb dot pods, then write push. Now we have this. Now let's run the command again. Okay, now you can see the command has run. Now again write dot elements dot pod, right? Okay, now element, what information does it require? It requires element data, then okay, so here we have created one dictionary in order to save different types of elements, right? So we have to add all the elements in the iterative way, so we cannot write like this. So let's write key, which represents the element type, and val in dot items. Okay, so here we are iterating through key and value of this element dictionary. Okay, so it requires element data, right, and the type. So here what we need to give element data. Here again we have to convert into tuple, and for the type we can directly give here as key. Okay, now let's run it. Okay, now we have created the part. Now we need to create one instance from this part. So again, go to the reference manual, search for the ODB instance or ODB instance again. So how do we create the instance? Session ODB is root assembly instance. So this is the path, right? So this portion we have as sub ODB dot root assembly in the instance. Then what information does it require? First it requires name. What is the name? It will be instance name. Okay, then the second information it requires is object. Object is what? Part, obviously. From the part only we are creating the instance, right? Okay, so local coordinate system, there is no local coordinate system. Okay, now execute this one as well. Okay, now what we need to do is we need to update and save the ODB. Sub ODB dot update, then save, then close. In order to see all the results, now we need to close the ODB and open it again. Okay, so we can use similar way we have opened the main ODB, so same method we can use to open the sub ODB as well. So sub ODB, so here I open ODB, name here it will be sub ODB. Okay, let's try to execute this. Okay, perfect. You can see the sub ODB. Because we have added just the bush, you can see only one part, and you cannot see any field output because we have not written anything to it. So this code we have written for single instance, right? So let's generalize this, or let's say iterate over each instance. So let's give tab here and just iterate over every instances. So for SN name in instance names, right, and instead of this one, instead of bush one, use this one. Now what we'll do is we'll run the script again. So before that, let's close the sub ODB. Okay, and at the end let's write some message Hey, we created a subdb, right? At the end. So let's go to this message area and try to run the script. Wait for a minute. Ding ding ding. Oh yeah, yay, we created our subdb. So now the subdb already open. Okay, you can see the subdb is open. Here you can see odb subodb.odb, and one more thing is there is no field output here. Okay, so that's it for today. In order to support me, please like, share and subscribe. So in the next video we will see how to write the field data to this subodb, and we can visualize this as a contour. Okay, so here is the GitHub link where I have saved the Python script that we have created in this class, the odb file, and also this explanation PPT. So till then, stay tuned to the channel, support this channel if you like my content. So thank you and have a great day.